Good afternoon, student. So welcome to the live session of the course on optimization methods for civil engineering. And this is the second live session. So in the last session, we have clarified some of the doubts of the earlier classes. And after that, so we have covered mainly this portion, that constraint optimization 2 and constraint optimization 3. So here, basically, we have discussed Lagrangian multiplier approach and Kuhn-Tucker condition. So this is constraint optimization with equality constraint and inequality constraint. And also we discuss about penalty parameter method. So where a constraint optimization problem can be converted to an unconstrained optimization problem using penalty approach. So that we have discussed. And then I introduce you with the meta-heuristic optimization method. So here we have actually said that there are several meta-heuristic optimization methods, and basically we also discuss means the genetic algorithm. So in genetic algorithm, I have discussed in 3 parts. That is simple genetic algorithm or SGA, and we also discuss about real coded GA, and then how you can apply genetic algorithm for multimodal function. So this actually one of the biggest advantage of genetic algorithm. Here what you can do basically that in case of a multimodal function, so where you have more than one optimal solution, and you can apply GA and you can capture all the optimal solution of the problem. So that is we have discussed how you can capture the global optimal solution as well as local optimal solution. So as I have discussed, generally ZA will give you the global optimal solution. If your problem has local optimal solution along with the global optimal solution, so in that case, ZA will give you the global optimal solution, but with simple modification of the algorithm. So what we can do, we can also capture the other local optimal solution. So that I have discussed. And then for solving genetic algorithm, so what we have we discuss about R programming. So you can use R programming and you can solve a ZA problem. So already the genetic algorithm function is available in R. So I have actually initially introduced R, that how you can install R, then how you can write a simple code in R, and then how you have solved a optimization problem using ZA in R. So that also I have discussed. So here in the live session, so I will discuss mainly few that aspect. So here so one issue is that that some of the students are asking that how to select an initial solution when we apply the classical method. Okay, so how to select an initial solution. So as you know, that when you are applying classical method, so you have to give an initial solution. Okay, so you have to give an initial solution. So, but how you will give an initial solution? So here I have shown you mainly 3 function here. So here 3 functions. About first function, so this is a convex function, and second one is a non-convex function, and we have 4 optimal solution, and third one we have several optimal solution. Now we just see the selection of initial solution is very important. Suppose for the first problem, because this is a convex function, and therefore you can select any initial solution and you will get the global optimal as well as the local optimal solution. There is only one optimal solution here, and that solution you will get if you are selecting any initial point. But in the second problem, here what will happen that if you are selecting a solution somewhere here, you may get this particular solution, but if you're selecting here, you may get this particular solution. So therefore, in this case, the solution, whatever optimal solution you will get, that is highly sensitive to your initial solution. And third one is basically we have a lot of optimal solution. You just see to get the initial or to get the global optimal solution, so you have to select the right initial solution. So what I will suggest, if your problem is a convex, so you can select any initial solution, but if your problem is a non-convex, then you should try with different initial solution and just see whether you are getting a better optimal solution. So that means you have to do some trial, maybe taking some different initial solution, whether you are getting a better solution. So I have solved this problem in the class itself. Suppose for this particular problem, I have solved using steepest descent method. So what I'm doing here, so this is the initial solution. Then I have chosen this initial solution. This is 1, 1. And what I have done, I have calculated the gradient, and that is the direction, negative of the gradient, and that is the direction here. And now if you calculate gradient at 1, 1, so you will get 2, 2. And that is the gradient value, and negative of the gradient is -2 and -2. And if you are applying these things, so x1 equal to x0 plus alpha d, and you are getting 1 minus twice alpha and 1 minus twice alpha. And if you put in this equation, and then finally you are getting this equation, and if I solve it, I'm getting alpha star, that is the optimal value of alpha is half, and I'm getting this solution. So here is the C, this is the optimal solution of this particular problem. So now I would like to show you, if you change the initial solution, then what will happen, because this problem, as I said, this is a convex function, and therefore if you are changing your initial solution, then also you will get the same optimal solution. So let us try with different optimal solution, and this is 2 and 1, and just see if I calculate gradient, this is 4, 2, and this direction I can also write 2, 1, and finally direction I am getting negative of the gradient, which is -2 and -1. And then if I put it in the equation 1, and finally if I solve it, and I will be getting the value of alpha, that is the optimal value of alpha is 1. So then if I put it, then again I'm getting the same solution. So therefore what will happen, if your problem is a convex problem, you have only one optimal solution, then you can select any initial solution and you will get the optimal solution, as well as that is the global optimal solution, because you have only one optimal solution of this problem. But as I have discussed for this particular function, so for this function, because this is a non-convex problem, so here you have to try with different initial solution. But if your problem is a convex problem and your function is a convex function, so in that case you can take any initial solution, you will get the optimal solution of this problem, and that optimal solution is a global optimal solution as well as local optimal solution. I hope this is clear. This is one of the doubt. Now let us see that I have discussed this penalty parameter approach. So this is a constraint optimization problem. So this is a minimization type, and there is a constraint that x is greater than 3. Then what I have discussed, that I can convert this problem to an unconstrained problem, so using penalty parameter. So here what is happening so this is the unconstrained function I am getting. So this is the f, capital F is the unconstrained optimization unconstrained function. Now here this particular method is your exterior penalty method. That means we are penalizing the infeasible solution. That means this is the infeasible solution, and we have penalized the infeasible solution. So now here what may happen, that you can take any initial solution. That means your initial solution can be on the feasible region as well as it can be on the infeasible region. So there is no restriction here. So you can take any initial solution. But recall the other method. Suppose in this method, so this is the barrier method, or what I have used basically. So that is the penalty function is 1 by zx. Now here the limitation of this problem is that you have to start, or your initial solution should be on the feasible region. So in this case, we have penalized the solution in the feasible region. So therefore, you have to in this case, so you have to start your algorithm from the feasible region. That therefore the initial solution should be a feasible solution. So then I actually explained that things in the class, that in this case, so you have to be very careful because initial solution should be a feasible solution. So what we can do, we can write a problem, we can write a different problem, optimization problem, to get a initial feasible solution. Okay, so you have to be very careful in this case because you need a feasible solution to start the algorithm or start the iteration. I have then there is another confusion that is a minimization problem. So I have discussed when I discussed genetic algorithm. So I said that a minimization problem can be converted to a maximization problem using. So it's a minimization problem. I can convert it to maximization problem 1 by fx. So here what we are done. So maximum fitness value. So this is the fitness value of the minimization problem. And once you are converting, that maximum fitness value is 1 by 1 plus fx. So fx can be 0 basically, and 0 then you will get 1. And now then the minimum one will be actually, so it will be 1 by, suppose fx is 1000, then it will be 1 by 1001 basically. So that is the basically minimum value. So you can then the question is why not 1 by fx? So if you're using 1 by fx, so when it's a minimization problem, so in that case, what will happen that if you are using suppose it is near to 0, this value will be infinity. So therefore, in order to avoid that one, what we do basically, this is 1 by 1 plus fx. So I can also write 10 by 1 plus fx, or any value I can take, but not 1 by fx, because when fx is 0, then it will be the value will be infinity. Okay, so therefore we are using 1 by 1 plus fx, not 1 by fx. So I hope this is clear. Then there was some confusion that how to select crossover and mutation probability. Okay, so I said that generally crossover probability should be high, so it may be around 0.8, 0.9, 0.7, something like that, but mutation probability should be very low. Okay, so we have to understand actually what is the function of crossover and mutation before selecting the crossover and mutation probability. So this is the single point crossover. So I have discussed. So here there are two parents, and basically then this is the crossover side, and after crossover I'm getting these two children. Okay, so C1 and C2. Now let us take this example problem. So these are the two strings. Okay, so this is the value, the function value is 23, and here it is 37. Now after crossover, so this is the crossover side, and after crossover I'm getting 22 and 39. Okay, now just compare the parents and the children. So here what is happening after crossover, I am getting a solution which is near to the parents basically. So you just see this is 22 I'm getting, and earlier it is 23. So one parent was 23, and after crossover I'm getting 22. That means I'm getting a solution near the parents. Similarly, it was 37, and I'm getting 39. That is also near the parents. So what you can conclude, that crossover is giving you a solution near the parents, or you can say this is a local search. That means you are searching near the parents whether there is any other better solution. So it's a local search you are doing. Now let us see what mutation is doing. Suppose this is the mutation, that is I'm going bit by bit, and finally this particular bit is mutated. Okay, and then suppose in this case, so it was 22 and this bit is mutated, and finally what you are getting 16. So you just see from 20 to 16, 20, that whatever new solution you are getting, that new solution is near not you're near this particular solution. That means you were searching a solution away from the current solution. So you just see the purpose of crossover and purpose of mutation is different. Crossover is basically doing the local search. It is searching near the parents whether you have any better solution. But what mutation is doing, mutation is trying to search the other unexplored region. Okay, if you have any better solution. So therefore, what we will do basically, so in order to have a very steady convergence, so I have to keep this crossover probability very low. Otherwise, what will happen? It will go from here to here. So maybe one region to another region. So it will just like a random search. So therefore, in order to have a very decent search process, so we are taking crossover probability very low, but sorry, crossover probability is very high and mutation probability is very low. And general this thumb rule is, suppose you calculate the number of bits you have. Suppose number of bits are string length is L, and then mutation probability should be 1 by L. Idea is that in a particular string, so you will be mutating only one solution. Okay, so that is basically you will do. I hope this is clear. So how to select crossover probability? Suppose the string length is 10, then mutation probability can be 1 by 10. String length is 1 by 100, the mutation probability can be 1 by 100. So this is the thumb rule, and crossover probability you can use around 0.9, 0.8, 0.7, yeah, like that. Even 100% crossover probability also you can use. Okay, so 99 or 95%. I hope this concept is clear now. So here I'm just trying to show. So this is the global optimal solution. So your solution is somewhere here, and if you are applying crossover, you will get either this solution or this solution. You will not get this solution. So therefore, you need mutation to overcome this region and to explore the other region. So mutation is necessary. Otherwise, if you are applying crossover, so you are just searching near the parent, so you may not get this global optimal solution of the problem. Now, there is another confusion that what is the need of identifying all the local optimal solution in case of a multimodal function? Okay, because we generally we want to calculate the global optimal solution, but what is the need of local optimal solution? I explained that for this particular problem, if you are applying genetic algorithm, that simple genetic algorithm, so you will get the global optimal solution. Okay, solution of this particular problem. But there are some local optimal solutions. So this is one solution, this is one solution, this is one solution, this is another solution. Now, what is the need of obtaining the other optimal solution? So this is the global optimal solution, and now suppose you are telling suppose you are giving the solution to the decision maker that this is the solution, and if you are taking that solution you will get maximum benefit. But during the discussion, if there is another constraint is coming, suppose in this case a constraint is there that x should be greater than 0.2, then what will happen? You have to run your program again with this constraint. But if you know the other optimal solution of this problem, and there itself you can say that there are some other, if this is not acceptable to you, to the decision maker, you are telling that if this particular solution is not acceptable to you, there are other optimal solutions. So this is next best solution, this is next best solution, this is next best solution. So you can choose out of that. So therefore, if you have the idea about the other local optimal solution, it is always beneficial. So you can tell that this is the global optimal solution, but I have some other local optimal solution. And if this solution is not acceptable because of some other reason, so in that case, what we can do, we can also go for the other solution. So therefore, there is a need to identify the local optimal solution of the problem as well as the global optimal solution of this problem. And this is the great advantage of genetic algorithm, that in a single run you will be able to obtain all the local optimal solution of this problem. So just see that I would like to solve this problem using classical optimization problem. So what will happen that if I say, take a initial solution somewhere here, I will get it. If I take it here, then I will get this one. And if I take it here, I will get this one. So therefore, if you are selecting a wrong initial solution and you also don't know actually what should be the initial solution. Okay, so in that case, you may not get the global optimal solution of this problem. But if you are applying genetic algorithm, you are not only getting the global optimal solution, you are also getting the local optimal solution of this particular problem or of the problem who have actually more than one optimal solution. Now there is another concern. What is selection pressure? Okay, so biologically or the definition of selection pressure is it's an external agent which affect an organism's ability to survive in a given environment basically. So it's a basically it's an external agent which is basically putting a challenge to the organism when they are trying to survive in a given environment. Okay, now just see that these are all solutions. So we have used, suppose here we have used the tournament selection. So in tournament selection, what I'm doing basically, so I'm taking a tournament size of 2 basically. So in that case, I have played. So total I have 6 solution, and then I have taken 2 solutions. So in the first time I'm getting 3 solution, and second time I'm getting 3 solution, and finally you are getting a set of solution, and they are basically winner. Okay, now you just see the 25 is the base solution. So what will happen that 25 basically that will win the tournament in both that time. So therefore you are getting 2 copies of this one. Now just see that if I increase the tournament size, that means now basically I'm asking that, okay, not 2 basically. So you select, you take 3 solution, and in that case what will happen, the 25 is the base solution. So therefore the 25 will have 3 copies. That means there will be selection pressure on the other solutions, and they will not be able to go to the next generation, and they will not be able to select because you are selecting 25. So what you are doing, you are putting selection the selection pressure. So and that is actually, so what will happen that if you're increasing your selection pressure, suppose in this case, suppose I am defining selection pressure in terms of number of tournament size basically, or tournament size, then from 2 to 3, that means you are putting more pressure, and 3 to 4 you are putting another more pressure. So in that case what will happen, all the solution will be saturated with the base solution, and you will get premature convergence. So you will not get, you may not get the global optimal solution of this problem. So I think you means you have understood what is tournament selection and basically how you will apply that one. So what should be the tournament size? So if you're increasing your tournament selection, if you're increasing your selection pressure, so in that case your entire population will be saturated with the base solution of that particular generation, and you may not get the global optimal solution of the problem. Okay. So here what is happening, the base solution will have 2 copies, then worst solution will have no copies, then other solution will have you will get 0 or 1 or 2 copies. But if you're increasing tournament size, that from 2 to 3, so in that case what will happen, the base solution will have 3 copies. Similarly, if you're increasing to 4, the base solution will have 4 copies. So that is not good. So what we'll do basically, so we'll use either tournament size of 2 or 3. So we'll not select more than that. So this is all about I would like to discuss, and if you have any question, you can ask me. I will answer those questions if you have anything. So if you have any question, so you can ask me. Or otherwise, I will close this session.
Excuse me, sir.
Yes.
Hello. Sir, can we say that number of copies the best solution can have after tournament is equal to the tournament size?
Yes, yes, yeah. So because the tournament size, if you are taking 2, that means tournament size of 2. So that the best solution will play the tournament 2 times. So he will get, means he will be selected in both the cases. So he will have 2 copies. Okay. So then if you're increasing to 3, then best solution will have 3 copies. Yeah.
Okay, but in the earlier assignment, actually, the accepted answers was different. So I thought, is it the same logic or different logic?
Which one? Which solution? I have to check in the assignment. Which one?
Assignment 7, question number 16.
I will check that one. Huh? I will reply to you. So what is your name? Manohar.
Manohar.
Okay. So maybe my TA will respond to your that question.
Okay, sir. Okay.
Yeah.
Okay. Thank you, sir.
Yeah. Thank you very much. So if you have any question. Okay, then as there is no question, so I would like to close this session here. So we'll meet again in the next live classes.